Hello everyone, my name is Hessam. I'm a PhD student at Rutgers University. My advisor is Professor Andrew Norris. The title of my project is Acoustic Transmission Between Water and Air using a three-plate solid metasurface, and I'm doing this presentation for ASA/ASJ 2025 press conference. So if we want to talk about the introduction, approximately 70% of the Earth is covered with water. So we should be able to communicate between water and air, and there are two main methods to do this: acoustic waves and radio waves. So acoustic waves, they are very great for water to water communication, but they are not great when we talk about water to air because there is a big impedance mismatch between water and air, and it causes 99.9% of the energy to be reflected at the water interface. The next method is radio waves. They are used for water to air communication, but the problem is that they use a lot of power to do this because the radio waves are attenuated rapidly in water. So what if we are able to actually address this issue and we are able to solve impedance mismatch between water and air? So if we look into the previous work done by other scientists, there are passive impedance matching mechanisms for water to air applications. Like for example, in this paper, you can see that they have placed this metasurface at water air interface, and they are sending acoustic wave through the mechanism, and some energy are transmitted. Actually, the energy transmission enhancement is almost 20-25 decibel, around 1200 hertz. So we see the improvement of energy transmission happens, as well as in the other paper we see that they are using this metasurface, and the acoustic transmission is going to like the sound pressure level has increased by 25-30 decibel. Without the metasurface, you see that the acoustic transmission is almost 0 to 10 decibel. So now we want to talk about the research objective in this slide. So this is actually the case without our three-plate structure at water-air interface, and this is actually our idea. We are placing the three-plate structure at water-air interface in order to be able to send acoustic transmission between water and air. So I have brought up the impedance ratio of water and air. So the formula of the impedance is density multiplied by speed of sound. So the impedance of air is almost 400 real, but the acoustic impedance of water is 1.510 to the power 6. So this is much bigger than 400 reals. And if we calculate the transmission coefficient between water and air is 5.3510 to the power minus 4, and the transmitted energy ratio between water and air is almost 0.11%, or 99.9% of the energy is reflected. And since we have done optimization for this structure, we have found the optimized values for H1, H2, H3. Like for example, these are the optimized value for the structure that work very well around 500 hertz, and the objectives for the optimization were higher energy transmission and higher frequency bandwidth. And you can see that the energy transmitted energy ratio is much higher, around 500 hertz. So for example, if I'm interested in seeing how this cell is vibrating, imagine that the incoming acoustic wave has this frequency of 482 hertz and 520 hertz, and those points are actually the points that have higher acoustic transmission between water and air. So we can look at the videos of how these cells are moving. So for example, you can see that the plate on the air side vibrates more than the plate on the water side, and they are more than the central plate, and the other frequency is that like literally the plate on the air side vibrates more than the other plate that on the water side, and the middle plate just moves translationally. And finally, thank you for listening. I would be happy to answer your question.
All right. Thank you so much for the presentation. We will now do some questions. So, Hesam, I'll have you, yeah, come off video. We'll spotlight
Hello,
you.
everyone.
Hi. And yeah, Wendy, go ahead whenever you're ready.
Yeah, sure.
Yeah, thanks so much for this presentation. As probably most of us here have experienced, if you try to talk underwater,
Yeah,
in
exactly.
the pool or somewhere else, you know how sound does not travel out. So we were very interested in this one. Um, we'll
Thank
kind
you.
of we have a few questions in the Q&A that kind of speak to this. So our first couple are from Richard, and um, the question is, what are the practical applications of this?
Like, for example, uh, in one of my pictures, I have shown that, like, literally, if a robotic vehicle underwater wants to communicate with a drone that is flying in the air, they cannot literally do that unless they come to the surface. Like, there is no real-time um, device that we can do this. Like, the design that we have done is like passive, meaning that you don't need to have batteries or any electronic device to put to float it on the water. So it's like a simple solution in order to be able to communicate between water and air.
All right, and what is the material like? Like for us average people who don't quite just in non-scientific terms, like what's the material like?
Yeah, sure. So one of the benefits of this structure is that it uses aluminum plates. So meaning that it is very common. You don't need to, create alloys or any specific material. It's very simple.
All right, and what would be needed to create the metamaterial? Because this is still a simulation at this point, right?
Yep, exactly. So one of the problems is that like the result that I'm presenting, like the equations that we have driven is true for infinite plates. So there is a difference between infinite plates and the real application, which is finite. Like when you want to create, it has to have a finite length or width. So we are working on a paper like a new setup in which the length of the plate is restricted, like meaning that, like for example, the length of the whole thing is like 2 by 2 meters, which means that we are able to actually manufacture that.
I gotcha. And then um, Richard also put into the chat one more question, and yeah, just wondering, um, we'd like a bit more info of what this would look like if we were looking at it. Like, what would this material be like, and what would it look like?
Yeah, so the picture that you see right there is the cross-sectional area. Like if like this is the structure and you cut it half, you see this structure. Like the ribs are continuous in the depth, right? So those columns that you see, they are in the depth, meaning that like for example 2 meters in the depth, and the structure, the plate, like they are continuous place in the depth for 2 meters, let's say.
All right, so this is like a cross section of what that material would look like.
Exactly. This is the cross-sectional area.
All right, and um, yeah, we'd like to dive a little bit deeper into that. Can you tell us, Richard is asking in the Q&A, but what's the white stuff in this cross section and what's it made of? And what's the black stuff made of?
So the reason that you see the middle one is black, like every element that you see regarding the structure can be made of aluminum. The middle one that you see is we have made it black because uh, we know that if we want to have less space, you can replace the aluminum with, let's say, a steel, which is heavier material. And what it means is that the middle plate acts like more mass. It doesn't really matter how it's bent. So it means that we can replace the middle one, which could be made of aluminum. We could use a steel material in order to create the middle one, and it's gonna have the same performance.
I think it's just this kind of like a metal plate that would go on the surface and it would be might contain different types of metals, whether it's aluminum or steel.
Yeah, the most important part is that it has to be stiff, like meaning that it's not gonna bend easily, like not wood or plastics. It has to be stiff, and as I said, if we use a heavier material like steel, it's going to be better for us. It's going to be better for the structure.
So like you were showing in your presentation, it would bend different ways. So it needs to not, it needs to be one solid piece of something that can do that. Is that what you mean?
Yeah, so exactly. Like in the videos that I showed, if you pay attention to the two plates on both sides, the plate that is on the air side definitely acts like a spring, like it bends, right? So we know in mechanical engineering that when something is bent more, it acts like a spring. It's gonna create a stiffness. And the other plate that is on the air side, it bends, but also it moves. So it means that the plate on the water side is a mixture of mass and stiffness, but the middle plate is definitely mass, so it doesn't bend. So it like if we want to have this structure to be working optimally, the middle one has to be very thick, or it has to be very massive.